So now we will introduce the convolutional neural network for task classification. We will apply in our natural language processing. So the CNN, as you know, it's originally for the computational vision task, but Kim applied the CNN to the problem in natural language processing and get a good result. So in this tutorial, I will introduce how to implement the CNN for NLP task. Now I'm using CodaLab, so here I need to connect to the my Google Drive. I already update the dataset to my Google Drive, and here we should also install the Spacey module, the English module. So the same we already used before. So you just put the comment here, then write. Then we import some important the necessary libraries. After that, we set the seeds and load the dataset. So I hope you remember you used this dataset before. This is assignment 3 of the supervisor learning, the block 4. So here we use this HappyDB dataset, and we will focus on the sociality classification task. This is a binary classification task. So and we already split to div test and set train div and test. And here we specify, we create our tokenizer as same the Spacey English module as a tokenizer. Then we get the field. So the field is the it's attribute in the touch text. We already use it. So you can take a look at the data. So the first column is a text. Second column is a label. So here, the first column, the first field is text. It's a sequential input, and the tokenized is a tokenized for English. We lowercase it, and the label is not sequentially, and we don't need the unknown token for the label. Okay, then we use Tableau dataset to load the split dataset, and this is my directory. You can change this directory to your corresponding directory. Then the file name, then format TSV, skip the head, and add this 2-column structure here. And build the vocabulary, same we build the text vocabulary and label vocabulary. It's binary classification, so label is 2, right? After that, we give to the bucket iterator to generate the batches, and we go to here to take a look at the input dataset. So to look at the first batch. So you can see we use a loop to look at the batch, and the first batch in the train iterator, we have Twitter and label, this 2 component. And first, the Twitter is text. The text input is 4 by 64. So 4 is sentence length. In this batch, the max sentence length is 4, and the 64 is our batch size. And the label size is 64. So the 64 is the batch size. So we have 64 labels, right? Okay, let's move to the CNN model for NLP. So in our input, instead of the image pixels, the input to most NLP task is a sentence or document represented as a matrix. So each row of the matrix corresponds to one token, typically word, but it could be character or bypair. We will introduce bypair in next week. And each row is a vector that represents a word. Usually this vector are word embeddings, such as the word to vector, glove, and you can also train your word embedding layer from scratch. So we always do that before, right? And for the 10 word sentence using the 300 dimension embeddings, we would have a matrix which is 10 by 300. Okay, this is for one example, one input. Okay, and in the vision, our kernel slides over the local patches of the image, but in NLP, we typically use a kernel that slides over the full row of the matrix. So that's the width of our kernel is same as the width of the input matrix. Okay, so the height of the kernel can be changed. So, but typically the sliding window over five word at a time. Okay, so let's go to more detail about this model. So this is example. So I think you already know in the class. This is example to implement the CNN. So let's see. So first, each input word is represented in a 5-dimensional vector, and the sentence length is 7. Hence, the input matrix of CNN is 7 by 5. It's here. So input we have 7 words. I love this movie very much, and we will represent it, this sentence in a 5-dimensional matrix. So this is 7 by 5. Okay. And here we use the third kernel. We use 3 kernels. We use 3 kernel range size. So so this means we have different different convolutional layers, and in each layer we have different kernel size. So here we will use 2, 3, 4. So this is our kernels. Okay, and in each convolutional layer we have 2 kernels. So every kernel will perform convolution on the sentence matrix and generate the feature map. Okay, what does this mean? First, this is one convolutional layer, but we have 2 kernels. So in this layer, we have 2 filters, 2 kernels here. Okay, those 2 stuff. And second thing, this is a second type of convolutional layer. We have 2 kernels here, and the kernel size here is 3. This one is 4, and this is another convolutional layer. Then we have 2 kernels here. In this kernel, its kernel size is 2, right? Okay. So we apply those 4 kernels on the input set. Okay. When we do the convolution, we will get 6 different output. Okay, and the output we will use activation function, then we will after the activation function, we will do the one maximum pooling to perform over each map. So this is a map. This is generated by this map. I think you already know it's by the convolutional operation, right? And the fifth, the software max linear layer. So it's same. We will do the max pooling on those maps, get the vectors, and we flatten the vectors here to pass through a linear layer. The linear layer will give us a prediction, this binary prediction. Okay, so let's move to the model. Let's build this model step by step. So first we need to create an input tensor and a label tensor. So first, our input sentence is this example. I like this movie very much, and we use text preprocess to tokenize the input and convert it to the tensor, and we can see what the tensor looks like. So it's tokenized to the word tokens, then convert to the index or in the dictionary. Then this tensor size is 7 by 1. So 7 is a length, right? And 1 is a batch size. Now we only have one batch size, so we only have one sample, so batch size is 1. And we also need to process the label tensor, right? So the label here, we assume the sociality is no, and because here only mention I like the movie, this statement not related to anyone else. So we think the sociality is no, and the token, the label preprocess will convert the token to the tensor. Okay, and tensor, this is the batch size. Now we only have one sample, so it's 1. And first layer is embedding layer. So in the embedding layer, we should embed each token to a 5D vector. So we will use this embedding module. I hope you're already familiar with it. We used it multiple times. So you can go to the PyTorch document to check the document about the embedding layer. Then you will get the you will initialize the embedding layer. First, you should give some hyperparameters to the to initialize the embedding layer. First is the vocabulary size. So you will get the vocabulary size from our text dictionary. Then we will embed the input to 5-dimensional vector. So the second element is 5. Okay, so when we get the embedding layer, we will feed the our input to the embedding layer, and this is our input shape is 7 by 1. Then when we apply the embedding layer on this input tensor, we will get embedding output. The embedding output should be 5 by 1, 7 by 1 by 5. So 7 the sequence length. First is the sequence length. Second is 1, and third is 5. Okay, yeah, I noticed this comment is wrong. We should switch these two lines, but yeah, I hope you know 7 is sequence length, the input sequence length 1 batch size, and 5 is the word embedding size. Okay, so now let's see, we already get this matrix now. It's 7 by 5. Now we should have 3 convolutional layers, but they are parallelly to process this input matrix and extract to get the new feature maps. Okay, so let's go to these convolutional layers. So I hope you already know familiar with the 2D convolutional layer. So we already used in the MNIST dataset to predict the digital in the handwritten images. And here, our input is also a 2D tensor for each input. Okay, each input in our case is 7 by 5 matrix. Okay, first things, we should match the input sets of the convolutional layer. So I permute this matrix here. So I will permute the move the first move the batch size as a first dimension, and followed by the sequence dimension and the embedding dimension. Okay, so here I use a permute. Okay, and we can see the permute is after permute it's 1 by 7 by 5, and we need one more dimension because the input tensor of the 2D convolutional layer, we need 4-dimension tensor, which is batch size by number of channels. So we need unsqueezed input channel dimension. And here, our input channel, we can say it's 1. We don't have any more other channels, right? We only have the word embedding for this input. So we set the channel equal to 1. And the height, so the height is our sequence length. Here is 7, and the width is 5. Okay, and let's see after the permute and the unsqueeze, our tensor already matched the tensor shape of the convolutional input. Okay, and same, we should initialize the CNN, the convolutional layer. So we need to specify some hyperparameters. So first, input channel here is 1, then output channel. And in our case, each convolutional layer will have will have 2 kernels. Okay, so this is 2 kernels, this is 2 kernels, this is 2 kernels. So each one has 2 kernels. So our output channel will be 2 here. Okay, and I mentioned you can consider this output channel as the number of kernels. Okay, and let's move to the kernel size. Okay, this is kernel size. In the previous tutorial, in the MNIST tutorial is 5, right? But in our in this CNN, we have 3 different region size. It's 2, 3, 4, and each has 2. So let's give the first kernel size. So here, because here we give two numbers here. As I mentioned, here we will not use a square kernels. We will use the kernels which has the same weights as input tensor. So the weights should be 5. Okay, but the height will be changed. So here, first the height for the first one is 2, and for second one is 5. Okay, and for the straight, it will be straight will be 1. So what that means? So we will use this kernel to apply on this first 4 element, then move down 1 to do the convolution. Okay, this is for the first convolutional layer, which kernel size is 2 by 5, and we apply the convolutional layer on the input embedding, then we get the output, which is 1 by 2 by 6 by 1. Okay, so what's batch size 2 is our output channel, and let's move this is 6, so you can use this formula to calculate what's the height of our output. So the input height is 7 minus the kernel size is 2. Add the we don't have the pad here, so it's 0 over 1 at 1 is 6. Okay, and same for the weights. So because we will use weight size as 5, so you can see the weight size will be 1. Here is 1. Okay, and this is output. Oh, this is 1. Actually, it is this one because the kernel size is 2 by 5. So the first output is this one. Okay, it is 2 yellow and brown output. Okay. Let's move on. So then we will give this output to a ReLU layers to add the nonlinearity. Then we get the output, and the output of the weights always 1. So because the weight of our kernels is same as embedding size in the NLP task, so we will squeeze the last dimension. So we don't need this dimension at all. After that, we create a new convolutional layer and a convolutional output, and this output comes from the convolutional layer, which kernel size is 2 by 5. Okay, and let's go to the second convolutional layer, which region size is 3, and and this layer also has 2 kernels. So we use the same method, same logic. We can create the convolutional layer, which input is 1, because we will also apply this convolutional layer on our input vector. Okay, so now we're here, right? We will also apply this 2 kernel on this input. So the input channel also 1. Okay, and the out channel is 2. We have 2 kernels, and the kernel size changed to 3 by 5. Stride is 1, and then we apply it, use a ReLU function, then we squeeze the last dimension, we get a new maps. So you can say it's 1 by 2 by 5. Let's go back to the image. So in the visualization, we create this one, and the output is 1 is batch size by 2 kernel output, right, the green, and each one has 5 element. Okay, so because we moved this window on this part is first, second, and to here it will be 5. Okay, and let's see here. Okay, we already have this one, and this is 1 by 2 by 5. Then we have the third one, which size is 4. The height is 4. So and also has 2 kernels. So we create the this convolutional layer, then apply on the same input. It's the input embeddings. Then we get a new output. It's 1 by 2 by 4. Let's go back to the visualization. Right, this is 4. Okay, and the height is 4, and we get the output. We have 1 input, batch size is 1, and 2 kernel. Okay, and 4 output. So you can try and move this filter on the input, and with straight 1 you will get 4 output. Okay, so that's the convolutional layer. After that, I also want to introduce advanced module in PyTorch. It's module list. So because those 3 convolutional layer not when you create this 3 layer, this 3 convolutional layer, they operate on the input embedding parallelly instead of sequentially. So you can creating these convolutional layers together, and you put all the sub modules to this list, and this list will process the input simultaneously. And this is, first you give a list. This is kernel size list, then the kernel number, so each one has 2 kernels, and embedding dimension, and the input channel, the number of input channel, and you instantiate the input, the module list, and in this list you have a in this function you have a list here. Okay, this is list, and we have a for loop. So we extract k, the kernel size, from our kernel size list. Each time we will extract 1 number. So first is 2, then the k equal to 2, then we generate a convolutional layer which has input channel number, output channel number is same, and the kernel size. So this k will be changed in the loop. Okay, each time we will get a new number. this k will be changed, and this list will contain 3 models in this case. And let's see, let's use a for loop to take a look at all the output from the 3 convolutional layers. Then you can see we use, okay, first we also need a for loop to process the list, to process the input embedding. So we extract each layer, the convolutional layer from the convolutional layers, okay, and use this convolutional layer to process the input embedding, then apply ReLU and squeeze the dimension, then we get a new output list. So let's see this output list. This output list, each one comes from the different convolutional layer, and you can see they are same as our previous outputs. You can see the last one, which kernel size is 4, right? And the output size is 1 by 2 by 4. Okay. And third, we go to the max pooling layer. Okay, so our converted output, we also call it the maps, are the size of batch size by number of kernel by size of height. Okay, and each sample is represented in a vector by each kernel. So the size of the vector is 6. Okay. So now, because we already removed the weights, so we only have the height here, right? The height. So we will use a one-dimensional matrix pooling here, and we will get numbers. The feature vector is generated from the 6 maps. Okay, you can see, take a look. This is our map, 6 maps, and we apply the 1D max pooling to get the 6 univariate vectors. Okay, for this one, we grab the highest one number. This one grab the highest number. Same here. Then we concatenate them to a single feature vector. Okay, let's see the code. Here we use a function. So the PyTorch function, which is max pooling 1D, and you can go to the document to take a look at it. And we give our first output, the convolute region 2 output, and which size, and we want to see the size 2. The third size is the last size, right? So we want to find the largest number in this dimension. Okay, so we print out this representation. It's maps. This is first, and this is second. Okay, and we want to get the highest number in this dimension, and in these 6 numbers. Okay, and first one is 1.69, we put it here, and in second element we find the highest one, x 0.67. This one is highest one, so put it here. After that, we get this output. This max pooling output is 1 by 2 by 1. Okay, and here we will squeeze the last dimension, which is 1. And as I mentioned, because later this output follow with the linear layer. The linear layer request the input is 2D tensor, so we squeeze the last dimension, and this output should be 2-dimensional. Okay, and same for the region 3 and 4. Okay, then we will get the same 1 by 2. So 1, same batch size 2 is a kernel number. Okay, and in the visualization we get 1 by 2 for first one, second one, third one, and we concatenate them together. Okay, so yeah, same. You can use the module list to do this process together. No, it's not here. Okay, yeah, actually you can use a loop to perform the matrix to do this max pooling on the convolute output. The same, the convolute output is a list. Okay, it's a list here, right? So you can use a for loop in the list, then do the max pooling on squeeze on each element of the list. Then we get a new list, which is a max pooling output. Let's print it out. So in this list, we have the same output as our previous output. Okay, so you can do this, and it's like some quick way, efficient way. Okay, and it's easier to organize code. So you can see we did this multiple lines, but we can use one line to achieve it. Okay. Okay, let's go to the concatenation. So we concatenate all the element. So each highest number from each kernel. So we will concatenate them together, then concatenate it on the last dimension. Okay, because first dimension is batch size, we will not concatenate on batch size. We should concatenate on the feature dimension. Okay, last dimension. Okay, after that we get the 1 by 6 concatenation. Let's go back to the image. Here, this concatenation is 6, right? We concatenate them together. Okay, makes sense? Okay, so let's move to the linear layer. So before linear layer, we will also use a fully connected layer. And okay, before the fully connected layer, we will use a dropout to avoid the overfitting. Same, use the dropout with the 0.5 dropout rate, and we get the dropout output. Then use a softmax fully connected layer, okay, to do the prediction. So you can see the input size should be the number of kernel region size. So how many region size you have by the number of kernel of each region size. So here we have 3 size, and each one has 2 kernel. So it's we have 6 features. So it's 3 by 2, and the output is 2. Because it's binary classification, so this linear layer will give us the probability across all the labels. Okay, so this is our final output from the linear layer, and same we will use a loss function and get a loss. Okay, so congratulations, you will already implement the sample CNN successfully. So let's build a class to solve our HappyDB problem. So here we define a CNN class, and we need several initial input. I already give some comment here, you can read it. And first, the input channel is 1, always be 1. And here, this is linear layer, you initiate, and the convolutional layer, we already mentioned, we can use the module list and use a loop to extract a different region size, and the dropout layer and linear layer. Then build a computational graph, the input to embedding layer, permute or unsqueeze it to do some to match the dimension, and the convolutional layer. Then we have the max pooling layer, concatenate, dropout layer, and finally we get the fully connected layer, and we return the final output. And here we instantiate the module and give some hyperparameters and send it to device. Initialize the weight, count the number of parameters, optimizer and loss function, training function, evaluation. Then we train it for 15 epochs. Okay, and I will save this checkpoint. So you should be careful when you run this code. You should already have this directory. You should create in your device. Okay, and then we run it, we get the output. You can see the validation accuracy, which can reach 89%. Okay, and after that, that's all about the CNN application on natural language processing. And I give you a small exercise so you can play with this architecture, and this is not a homework, you just have fun, and if you have any question to implement it, please tell me. Okay, thank you.